So welcome back, everybody. Hope you had a great week. The topic today is the detailing of the optimization methods, which we are going to implement in order to find the best possible energy minimum, so that we can then, when we have this energy minimum, we can then start the optimization part and the calculation of the expectation value of the energy with our grand Monte Carlo scheme. So what I wanted to give you today is first a reminder from last week and the derivation of what is essentially the fundamental equation which people use in basically all these optimization schemes. And that is Newton-Raphson's method. When we're done with that, I'm going to derive the equation for the gradient of the energy with a simple example, so you see the basic steps. And then when we've done with that, we are going to look at some methods which are called semi-Newton methods, which avoid calculating the second derivative of the energy. Because what we want to find are the roots of the gradient. So we want to drive the gradient to zero of the energy, because the energy is, in principle, a convex function, and we want to ramp up our large Monte Carlo calculation at the energy minimum. So we don't want to waste cycles away from the energy minimum, because these are points which are of no use for us, because we are away from the optimal point. So to find the optimal point, that means finding where we have the optimal values for the parameters of the trial wave function. And with that, when we have these optimal points, that's where we start the big Monte Carlo machinery. So the ideal now is that we will just use some few cycles, some few floating point operations on calculating the gradients, and hopefully we can get as quickly as possible down to the minimum. And then when we are at the minimum, we are going to launch the grand Monte Carlo scheme. So the steps today is first a reminder from what we had last week with the basic derivation of Newton's method, which is based on a Taylor expansion of the energy around an optimal value for the parameters. Okay? And then we are going to look at these methods, and at the end, we are going to look at the way we can implement the calculation of the energy optimization. Now, there is some additional material here where I link to a textbook by Boyd and van der Berge, which is a kind of standard textbook on optimization problems. And in most cases, the type of problems which we deal with in physics are problems where we have convex functions, hopefully. That's the kind of ideal we want to have. And then we know that the gradient has to be zero at the minimum, and the second derivative has to be positive. That's a typical definition mathematically of a convex function. And many of the functions which we encounter in physics are functions either of one variable, and then we know that if the second derivative is positive, then we have a minimum, or it could be represented by a matrix, and then the matrix has to be what we call positive definite, which means that all the eigenvalues of the matrix are larger than zero. So in our case, when we move beyond one parameter, we are going to have a matrix problem to optimize, where the different matrix elements are represented by the degrees of freedom we have chosen, the different parameters. And in that case, what often happens for the energy is that the energy is going to be represented by a matrix which is positive definite, which has positive eigenvalues. And that matrix is then something which leads to a second derivative, or what we call the Hessian matrix last time, which is a positive definite matrix. Now, this textbook has a series of slides, and actually quite many, more than 300, because they have compressed the textbook in a textbook of 600-700 pages. But the slides which are interesting here are those which deal with Newton's method and perturbations of Newton's methods, like those which we're going to study today. And you will see that the typical methods we will end up using is normally just a plain gradient method with some modifications, or a semi-Newton method. But the methods like the steepest descent and conjugate gradient descent require that we evaluate the second derivative of the energy function. And that second derivative, when we do a Monte Carlo estimation of the expectation values, is going to be given by 6, 7 different integrals with their possible errors. And normally we don't want to evaluate that. So the steepest descent and the conjugate gradient descent methods are methods which are useful if you can evaluate easily the second derivative of the function you're dealing with. So normally we actually end up with a plain gradient descent method or some modifications of that. And this is where we are going to put the focus computationally. So I wouldn't recommend, if you go to many variables for the wave function, to use methods like conjugate gradient descent, even though they are more stable and give better results with less cycles. So the problem which we have is always this one, to strike a balance between the number of floating point cycles we want to spend or we have available, because often you have available a given slot of CPU hours, and the precision of the calculation. And this is, at the end, it's you who has to strike that balance. Okay, so let's, what I'm going to do now is quickly to switch over to the whiteboard, and you will find a lot of the information in the slides, but I wanted to, as usual, to slow down the pace a little bit, and then we go straight into the whiteboard and remind ourselves of some of the things which we discussed last week. So let me quickly give you a short reminder from last week. So what we did was to look at a Taylor expansion of the energy. So the energy expectation value, which you can often find written in different disguises, this is a function of these parameters alpha. And I'm just going to quickly repeat some of these. We would often rewrite this as the expectation value in the more physics-like way. But I'm going to write this in a shorthand manner as the energy of an optimal parameter alpha. So this alpha can be a vector of parameters, or it can just be one parameter. So ideally, if alpha is just one parameter, then when we look at this function E of alpha, and we make a plot, and this is essentially what we are doing in the project, in the first part of it, there is an ideal here where we would start with some alpha 0. This is the first iteration. And then we would step down by calculating different gradients till we reach the final point here. And this is what we call alpha hat, which is the alpha optimal value. So in statistics, when you're looking at the optimal parameter, this is often labeled with a hat on. Then, if you now think of all these iterations which you make, where you are making guesses for starting point, so the method, the way it converges, depends very much on your guess for the initial starting point. And at a certain point, we end up with an A of K. And this quantity here is a quantity which we label as an alpha of K plus 1, which is given by the optimal value. So it means that we do a set of iterations, and everything here is based on a Taylor expansion around the minimum. That means a Taylor expansion around the optimal value. So let me quickly remind you of that Taylor expansion. So this is the overarching view on what we are doing. So if we now look at the Taylor expansion of this energy, when we now Taylor expand around a value alpha, which is the optimal one, we can then make an expansion around alpha plus minus an alpha k, which is the previous iteration. So remember now that we are thinking of alpha hat as a result of the k plus 1 iterations, and where we then have reached a convergence. So convergence in this case means that the gradient is zero, or as close to zero as it can be. So this means that when we think of this as vectors, what we have then is the energy derivative of, so this is a gradient of alpha of evaluated at the value k. So this is now a vector. And that's why I'm putting up this transposed. And this is multiplied with a vector of all the parameters minus alpha k, because this is how we are making the Taylor expansion. So if it's not a vector, then we would simply have if you have only one parameter, like the case here, then with only one parameter, this would just be d of e of d alpha, evaluated alpha equal to alpha k, and then multiplied with just alpha minus alpha k. And then these are just scalar quantities. But if you have more than one parameter alpha, you would rephrase this as a gradient times a vector. And since the expectation value of the energy is a scalar, it's just a number, then you have to take the transpose of one of these vectors. So when you then move on to higher derivatives, then you would have an alpha minus alpha of k transposed. And then we have the second derivative. So this is what we normally call the Hessian matrix of alpha of k multiplied with alpha minus alpha of k. And then we have higher order terms, which are then given by higher powers, alpha hat minus alpha of k. And this is a norm 2 cubed. And this continues all the way. So this is actually a norm 2 cubed. So this means that this has to be 3 times 2 here. And this continues to higher order, but what we did was actually to truncate this at the level of the second derivative. And this is what we did last week. So when we truncated at the level of the second derivative, at the level of delta E second derivative, then we could find a recipe where we now have this alpha of k plus 1, which is the optimal value. This doesn't have a hat. Let me just put it like this, equal the hatted value. And this is equal to an alpha of k minus. And then we have the inverse of the second derivative. And I'm putting alpha k because the second derivative is evaluated at this value, multiplied with the gradient, evaluated at alpha k. So the basic recipe is that we start with a given guess, alpha 0, and then we continue to iterate till we have reached a convergence. Now, this quantity, the second derivative, which we have here, this is normally called in the literature, it's called the Hessian matrix. This is a Jacobian, and it is a matrix then, which in our case is going to involve several integrals for calculating the second derivatives. Because just keep in mind now that the gradient of the energy is actually, in our case, going to be given by several integrals. So the problem which we face, so problems. One, we need, if we want to implement it as it stands, we need the second derivative at a given value alpha k. And if you have, let's say, 100 iterations, that means 100 alpha k values. It means that you have to calculate the second derivative 100 times. And then you have to invert a matrix. So one thing is that if you do 100 iterations here, but suppose you have 1,000 such parameters alpha. If you have 1,000 such parameters, this matrix here becomes 1,000 times 1,000 matrix. And if you do 100 iterations for each of them, that means that for each iteration, you have to evaluate 1,000 times 1,000 matrix, and you're doing this 100 times. So to invert a matrix like that one requires n cubed floating point operations. So this is typically something you don't want to do. The other thing, as you will see quickly now, when we calculate the gradient, this at the Monte Carlo level involves the evaluation of several integrals. So we need that one, and this is tricky to evaluate, and you normally want to skip it, and you replace that with just a parameter, because then it's easier, actually computationally easier, to run the calculations, the iterative calculations, with just guesses for these parameters, instead of evaluating the second derivative and then inverting a matrix. So the light went here. Yeah, I guess we can just put the backlight. Okay, then it came back. Yeah. Some black magic. Okay, so what we also need to think of here is that this is sensitive to the initial condition. And the initial condition is then this alpha 0. And you can see that quickly now, if your energy has some local minima, suppose the function you want to evaluate as a function of alpha looks like this. So ideally, you want to get this value. This is the alpha optimal which you want to reach. But if you start with an alpha 0 here, then when you iterate, you reach this point. And in that point, your gradient, d of alpha, is equal to 0. So that's a typical problem which you can face if you have a multidimensional function. Now, one thing which makes this a little bit easier for us is that normally the energy is a function which is pretty simple, and it has often just one global minimum. So that saves the day for us compared to many of the standard optimization problems where you can have many local minima. Another type of problem which we can face, if we now look at this function which we have here, is a situation like this. So this is normally when you go to many dimensions, it's something which we would call a saddle point. So if we start with an alpha 0 here, and then we iterate down, then we also reach a point which has a gradient which is equal to 0. And then our algorithm can actually be stuck in this point, or it can be stuck in that point. But as I said, one of the advantages with the expressions for the energy which we have, and you can see that from the plots of most of the expectation values which we have, and the code examples which are in the lecture notes, you will often see that the energy has just one minimum as a function of the parameters. And that's a very lucky circumstance, but it's not given that it may be like that. So we can have situations with the local minima, with saddle points, and we can actually be stuck in those. So just keep that in mind when we are now setting up Newton's algorithm. So what is common then? So this is sensitive to the values of alpha 0. And what we also often do then is that we replace the delta, the second derivative, with a constant. But the results are also delicately depending on how you can evaluate the gradient. So we can call this a delicate dependence on the evaluation of the gradient. So let's see how that comes through actually. But let me set up the kind of recipe which you would end up setting up. So the first simple case is just a plain gradient descent. This is what we call the plain gradient descent. And that means that the iterative process is run like this, an alpha of k minus, and then you have a parameter gamma, which in machine learning, for those of you who are familiar with machine learning algorithms, this is normally called the learning rate. This can depend on the iteration value, or it can just be a constant throughout the calculations. And this is then multiplied with the gradient of the energy evaluated at a value alpha k. Now, this gamma k is normally called a learning rate. And there are ways you can optimize it. So it can be set up with a k-dependent value. So it depends on some information about the gradients. This can be done if you do steepest gradient descent. So in steepest gradient descent, so let's just point that out. Steepest GD. So GD stands for gradient descent. So let's just mark that one here. GD. When you see that abbreviation, this is just a plain gradient descent. So in steepest gradient descent, this gamma of k is actually given by the gradient. So I'm going to use a shorthand here, so which makes life a little bit easier. So this quantity here is something which I'm going to label as a g of alpha of k, g for gradient. Okay. So this parameter can then be written out as a g of alpha of k is a vector of g of alpha of k divided by, and this is something which we actually derived last week, but we're going to bring it back this week. So we have alpha of k, and then we have this second derivative matrix. So delta here is now a Jacobian matrix of delta E multiplied with g of alpha of k. Now, the steepest gradient descent is something which I discourage using here, essentially because you have to evaluate the second derivative. So even if you can evaluate it and it's simple, like in our case in the variational Monte Carlo calculation, in project one, we have one parameter, so then it's a scalar. But even with one parameter, the evaluation of this quantity here involves something like 6-7 integrals, which are evaluated stochastically. So this quantity here, even with few variational parameters, is something which is pretty involved. If you have a simple analytical expression for it, you could do it if you have few parameters, but normally you would like to avoid performing calculations of this second derivative. So you can have a k-dependent value. You can use just a constant gamma. So that means that gamma of k, this gamma of k just simply goes over to a constant. And then you could set up an array in the calculations where you could have a gamma of k which runs from 10 to the minus 4, 10 to the minus 3, up to, let's say, 10 to the minus 1. And you run calculations and you pick the gamma value which gives you the best result. The best result means the closest you get to a gradient which is close to 0. So alternatively, this is actually the simplest approach, and you will see in the codes where we have examples of that. Alternatively, we can use optimizers, as they are called, and there are several optimizers, and there are several of these. One is called momentum, and we will mention that a little bit next week. This is a simple modification of the plane gradient descent. We have a method which are called root mean square propagation, which takes into account information from the gradients. We have a method which is called adaptive gradient, ADA-grad. And then there's a famous method in machine learning which is called ADAM, which is called adaptive gradient with momentum. And this method, ADAM, is a method which was introduced just for updating this learning rate, which was introduced back in 2014. And since it's so popular, it has more than 200,000 citations since 2014. And a good scientific paper has perhaps 100 citations. So if you have 200 citations in 11 years, that 200,000, that's quite something. So you would typically deal with optimizers. You could use a steepest descent, or you could use something, a more advanced method, a conjugate gradient descent. But these are methods which become often expensive because you have to evaluate the gradients. So some of the methods which are very popular, a method which we call quasi-Newton methods, which we are going to discuss also today. And here there is a whole plethora of methods. So one of these is called Broyden's method, which we will derive today. This is Broyden's method. We have another one, which is an acronym, which is called BFGS, where B stands for Broyden, F stands for, and now I have to remind myself about it because I never remember the name of all the different authors. So this is Broyden, Fletcher, Goldfarber, and Shannon. So there are 4 authors. So BFGS is a method you will find in SciPy, and we are going to look at how you can encode this kind of quasi-Newton methods with scientific Python. You have other methods, options like Powell. These are iterative methods which make an estimate of the second derivative. So all these methods which you see here, they try in one way or the other one to estimate the second derivative for you without calculating it. So these are estimates of the second derivative. And we are going to look at the basic way of making an estimate of the second derivative of Hessian matrix. Now, one thing which I want to do now, before we move on, is to set up the expression for the calculation of the gradient. And then when you see this expression, then you understand why these are very delicate calculations and why you don't want to calculate the second derivative. So if you now look back and we are setting up the algorithm, so you need to initialize gamma. You have to set some initial value. You have to fix the number of iterations. Then you need initial value, need initial guess. Alpha 0. You also need to choose method for updating gamma. So in here you need plus method for updating or not updating gamma. For update. So when you have that, what you would do then is to have a while loop, which then runs like while number of iterations smaller or equal max. So this is something you fix, or gradient delta E, the quantity you want to calculate, is larger than a given number which you have chosen. So you will never get, and you will see that in the applications, you will never get a gradient which is close to 0 or 0. But you will get something which is 10 to the minus 5 or 10 to the minus 4. And then it's you who has to decide when you stop. So you keep iterating while these conditions are met. And then you will then calculate the gradient, calculate the value alpha or delta E at a given alpha for the iteration which you're doing now. And now I'm just going to call this for I, alpha y. And then you update I. So you do I equal I plus 1. And then you calculate alpha of I plus 1 is equal alpha y minus this gamma multiplied with your gradient. And this is n while. This is the basic method you're going to implement. And you can replace everything which you have here. You can replace that one with a function from SciPy or other programs. Can replace with SciPy. Let me just write that one correctly here. With SciPy, for instance, SciPy.optimize, and we are going to look at an example on how you can do that. Or you can have your own function for the optimization part. If you're using a conjugate gradient or if you're using other methods, I mean, feel free to do that. But I would recommend in the beginning that you either use the SciPy optimize function, because we are not going to have so many parameters. But what we need is the gradient. So we need this. And let's look at the equation which you need to code now. Okay? Because this is something which we need to plug in our codes. So let me just bring it back here in case you didn't have time to write it down properly. Anyway, the whiteboard notes are always uploaded online, so you can always look back at them. So what we need now is the gradient of delta E as a function of alpha. So let's just take away this alpha k here. Now, let's just look at a simple example with a function which is real. So the example which I'm setting up here, a simple example with a real y function. Remember now that the wave function is a complex function in general. So the simple example which I'm going to look at is a function where we have, which we have seen many times before, and that is equal to our psi trial of x as a function of the variational parameter. So this is the typical example which we are dealing with in project number 1. So what we need now is to remind ourselves for the expression for the energy. So the expectation value is simply going to be given by a d of x. So this is a one-dimensional object which we're looking at. Now, our wave function doesn't have any complex variables. So when we write c of t of x of alpha, we know that this one is equal to the function itself. So this is going to simplify some of the mathematics here. So a simple example could be a function like that, but just keep in mind that in general, this is complex. So when I look at the Hermitian conjugate, then I have to be careful. But the example which I'm going to run through now is going to make life a little bit simpler. So I have h, the Hamiltonian, which then acts on psi of t of x of alpha. And this is divided by the norm, because we are not making an assumption that the wave function is normalized. And for the harmonic oscillator, which we have here, this would just be the wave function squared, which is pretty simple. Okay, so we don't need to specify the Hamiltonian, but now we just need to take the derivatives. So if I take the derivative of this quantity, so we have only one variable, but in general, this would be a gradient. So what we need now is a d of e of alpha, of d alpha, and I'm just going to write this as a d of e of d alpha, just for simplicity. Now, if you now take the derivatives, we're just going to need to use the standard rules for calculating derivatives. So if I now look at the equations here, since my wave function, the complex conjugate wave function is equal to the wave function, I can actually skip all these complex conjugation symbols. Is that okay? But at the end, when you're dealing with a more complicated, a more realistic function than just the harmonic oscillator, which is a simple case for the ground state, we are just looking at the ground state now. So if you're looking at excited state and you go into different spatial dimensions, like 2 or 3 dimensions, then you know that you will have, if you transfer this one to, let's say, spherical coordinates, the wave function will have a complex part multiplied with a real part. With a spherical harmonics, yeah?
Yes. Yeah, this transfer equation works for the constant.
You can also have for harmonic oscillators, if you're dealing with Cartesian coordinates, the harmonic oscillator itself is given by real functions. But if you go now into spherical coordinates, then your function will be a solution of a radial equation multiplied with the angular part, which is given by spherical harmonics. So depending on the basis you have, some of the wave functions need not be given by complex functions. So here we're just looking at a simplification, but then when you do the formal derivation, you're going to get the same equation for the derivatives at the very end. It doesn't matter, but then we need to use the hermiticity of the wave function, of the Hamiltonian operator and the complex conjugate. But now we can just deal with this as real functions. So the harmonic oscillator is a very simple case. And if you think of, if you go back to what you had in basic quantum mechanics, you know that the solution of the one-dimensional harmonic oscillator contains a term like this, multiplied with a polynomial, which is called a Hermite polynomial. And these Hermite polynomials are just functions of x to given orders. So let's look, if we now take the derivatives of that function here, we will have a first term, so we get a factor of 2 because we have the wave function squared, and we're taking the derivative with respect to the parameters alpha. So the first term is going to be given by a d of x, and then I have a term which goes like d phi of alpha. So I'm simplifying a little bit here now. So my phi of t of x of alpha, I'm going to make it a little bit simpler. It's just replaced by a psi of alpha. So this is simply just to avoid all this notational clutter, okay? So when you see this psi of alpha, this is simply the derivative of the trial wave function with respect to the parameter alpha. So this is a d of alpha. I'm going to have an additional expression which goes like psi of alpha. And this is multiplied with my h, which then acts on psi of alpha. So this is one term, and this term is then divided by the norm, where I have a d of alpha and psi alpha squared. Then there is an additional term here. Sorry, this should actually be, I wrote this wrongly, so sorry for that. There should be a term which goes like 1 over psi alpha, like that, plus minus, and then there is a new term which goes like 2, and then I'm just using the standard rules for the derivatives. So I'm going to have a d of x, and then I have my psi alpha. In principle, this is complex conjugate, but we don't need to deal with that now because this is just given by real functions. And then I have my d of x of psi of alpha squared. So this is one term, and this term is multiplied with,
Yes, the transition from the pages are still in the same energy equation.
So what I'm taking now is taking the derivative of this quantity, and now I have to go through. So there will be a term, which now when you take the derivatives, you will get a term where you take the derivative of this one. But then you also need to take the derivative of that one. And then you use the hermiticity of the operator which you have. So this one will obviously give rise to this term which you see here. And what I need next then no, sorry, this should be, this is me just being wrong here. This is psi of alpha. And in our case, this is actually given by this quantity. So what I'm doing now is simply to take the derivative of this quantity here. And that has this term here divided. So what I need then when I'm setting this up is now a additional term here where this one is squared. So this is just a plain, because I need to take the derivative of the denominator as well. Okay. So when you then have the minus sign, that's the term where you look at the derivative of this one, then this is unchanged, as expected, right? But then I need the derivative of this quantity. And what I get then is an additional term, which then goes like a derivative of d of x. So what I'm doing next now is also to split up this term, which you see here. This term is now split into a term here. And then I have the next term here, which now contains a psi of alpha multiplied with a d psi of alpha of d alpha. And this term is also divided by d of x of psi alpha squared. So the second term is the one which is a little bit interesting to look at now. So let's look at this term which we have here. So one thing is that this is nothing but the expectation value of the energy, as before. But if we look at this one, we see now that we can actually rewrite that if we also remind ourselves that this P of alpha of x is equal to the probability of psi of alpha of x squared divided by the norm of dx of psi alpha of x squared, like that. And then what we can also do, if we now look at the equation which we have here, if we take this second term, let's just elaborate a little bit on that one. So the second term in that equation is given by a d of x, and then I have a psi of alpha multiplied with a d psi of alpha of d alpha, and this is divided by d of x, second term in last term, or the second term of the second term squared. If I look at this one, what I can do now is simply to multiply with psi alpha and divide by psi alpha. Okay? So if I then have psi alpha times psi alpha here, you see now that what I'm getting is actually psi alpha times psi alpha here, and then I have the denominator. So that means that I can rewrite that term as a probability. So I can then rephrase this one as an integral where I now have the probability of this P of alpha of x. And then what we have next is 1 over psi of alpha of d psi alpha of d alpha. Now, this term, the last part here, which you see, is something which we can rewrite in a very convenient form now. Because remember now that the wave functions which we are looking at, they are normally given by exponentials. So a standard trial wave function is now something which follows a simple parameterization which we have chosen, and many physical, the solutions to physical equations like the harmonic oscillator or the hydrogen atom or many of the other kind of trial wave functions which we end up with, due to the form of the potential which acts on the system, they often have solutions or minimal parts of the solution which look like an exponential with some arguments. So if you then look at the second term here in that equation, then if we just do that before we take a break here, this d psi alpha of d alpha, this is actually the derivative of the logarithm of psi alpha. And in many, many cases, actually in most applications, the trial function which we actually end up with is given by some combinations of exponentials. Then this psi alpha is proportional to some exponential, which is a function of alpha, of x, and other variables. And then you see that calculating the derivative then means that if we have the log of an exponential, we often end up with simpler expressions for the derivatives. So in our explicit case, in project 1, and if we look at the harmonic oscillator, then we have that psi of alpha is actually e to the minus 1/2 of alpha squared x squared. And then we know that ln of psi of alpha is nothing but minus 1/2 of alpha squared times x squared. So calculating the derivative of that quantity becomes then much easier. So this is an advantage of the parametrizations which we do. So if you then look at that second term which we had, this term here, you see now that this is nothing but an expectation value. So this is the expectation value of this quantity here, because we have a probability times a variable. So we can actually rewrite this as an expectation value. We know that if we go back again, this is the expectation value of the energy. This is something which we now can rewrite in terms of another expectation value. So when we collect everything, then we can actually show that the derivative of E with respect to alpha is given by 2 times the expectation value. And now I'm just going to use this kind of physics way of writing the expectation values. And this is going to be the expectation value of d ln of psi alpha of d alpha multiplied with the local energy minus the expectation value of d ln of psi alpha d alpha multiplied with the expectation value of the energy. And this can be made general to the gradient as well. So if we have more than one variable alpha, then we have to evaluate the gradient, but the expectation values which we have to calculate are the same. So what we end up with is actually 3 integrals. And these 3 integrals have to be evaluated using Monte Carlo methods. So these are 3 integrals. One we already have. So we have this integral here. But we need to evaluate this integral, and we need to evaluate that integral. So we have 3 integrals to evaluate. Integrals, and then we're going to take a break now. 3 integrals to evaluate. Using Monte Carlo sampling. Now, it sounds like we are introducing a considerable complication. However, we are going to evaluate these integrals with fewer cycles than the large Monte Carlo calculation. And the hope is obviously that these evaluations, which you see here, are going to give us a pretty good estimate of the gradients. So with the expression for the gradients, what we can do, and this is what we will do after the break, we are going to look at how we can encode that in a code example. So this is something you will have to add in your programs. So after the break, we're going to look at how we can implement it using that kind of example, which we have been running through during the lectures. And then after that, we are going back and we are going to take a look at another method, which is then called Broyden's method, which is this one. And we are going to scratch the surface of the Broyden-Farberg Goldberg-Shannon method. So these are very popular methods which try to circumvent the calculation of the Hessian matrix. Not pretty clear? So it's not so difficult to actually show that this is the case, this equation which you have here, that this also applies to a general wave function which is complex. Then you simply have to use the hermiticity of the Hamiltonian and just run through the derivatives. But the basic equations we have to program are these ones. Okay, long way to get there. So let's take a small break. So welcome back. So what we did before the break was to, one, bring up a reminder from last week about Newton's method and how that gets converted into a simplified version, which is just called the gradient descent method. And everything is based on, believe it or not, a Taylor expansion around an optimal value. And since we have more than just one parameter in general, we are going to end up with vectors and matrices in the Taylor expansion. But for project one, we are going to live with just one parameter for most of the project. And that makes life much, much easier when we are setting up everything. So what I want to do now is to show you that example, which is in the lecture note. And then when we've gone through that example, we are going to go back and look at the quasi-Newton method, which is called Broyden's method, which is one of the basic stepping stones towards ways to circumvent the problem of calculating the second derivative. So you will see that people have dedicated their research lives in mathematics and numerical mathematics on actually trying to circumvent the problem of calculating a second derivative. And in the field of machine learning, these type of problems, they are just the basic building stones of every machine learning algorithm. At the heart of every machine learning algorithm, there is an optimization part, because we have a set of parameters and we want to find the optimal parameters. So this kind of optimization problems, they pop up in essentially all applications of specific science problems. So let's take a look at the Jupyter notebook then, and then we go back to the whiteboard. So the Jupyter notebook for this week, you will see the first part here just is more about the mathematics of these different methods, which I normally prefer to cover through the whiteboard. But if we scroll down, so the steepest descent is one of the more popular methods. There are some repetitions of convex functions, etc. But these are things which you probably have seen in different mathematics courses. And if we now go more into the program itself, so there are also ways to implement these methods. The conjugate gradient method is a method which we normally discourage using because it requires that you can calculate the second derivative. And you see now already that by calculating the standard derivative of the energy, you have 3 integrals you have to evaluate. If you want to calculate the second derivative, you're going to end up with 6 to 7 integrals to evaluate stochastically. So you simply don't want to do that, period. So the first thing we are going to look at now is an implementation of this equation here. So this is the derivative, but you would not write it out like this because your function is normally, the trial wave function is an exponential. So you would actually take the derivative of the log, as we discussed before the break. And then this integral, and then we have this one, which is a derivative of the log of the trial function, and then the expectation value of the energy. So in order to calculate the gradient, which is written in this compact form here, we need to evaluate these integrals. So if you look at the program here, this is something which I've seen before. So this is 2 electrons in 2 dimensions, and there is a Coulomb interaction which acts on the system. So what I did now was to set up the problem here as we did before. So this contains importance sampling as well. So you have the trial wave function. This is the harmonic oscillator plus a correlated part, which we are not dealing with now. So the first element here is just a plain harmonic oscillator. Then I have an analytical expression for the local energy. So I don't need to evaluate the second derivative. I have the derivative of the wave function, which is now the derivative with respect to the variational parameters. So this quantity which you see here, this one, derivative ansatz, is derivative W ansatz, derivative of the wave function ansatz with respect to the parameters alpha and beta. So what I'm calculating there is actually this quantity here. So the entry point, so the argument, okay? And then, so I'm hard coding things because I have an analytical expression for that. So this is the derivative respect to alpha, and this is the derivative respect to the parameter beta. And now I'm utilizing the fact that I'm calculating the exponentials and then taking the log of the exponentials. So this gives a much simpler equation. And as we said before the break, most of the ansatzes for the wave functions look like exponentials with some arguments. And that follows often by you imposing a minimal condition of the wave function. So if you have an electron which is being attracted by an atomic nucleus, there is a 1/r potential from the atomic nucleus. There's a 1/r divergence in the kinetic energy of the electron, and these two have to cancel each other when r goes to 0 in order to avoid divergences and to have energies which diverge. So the energy is a constant quantity. And then that puts a minimal constraint on the wave function, which goes like an exponential with some arguments. So in a certain sense, many of the classical physics problems you encounter have minimal constraints on the wave function, which make it look like an exponential times something. So I'm using that feature here. And the next piece is a quantum force, which we discussed some 2 weeks ago. And then I have my energy minimization, where in this case here now I just do a 10,000 Monte Carlo cycles. And then I'm using importance sampling. And you will see now that I'm actually setting up 2 numbers. One is the energy derivative. So that's the quantity I'm going to return. This is my gradient. Then I need this integral for delta psi. And then I need the derivative of the trial wave function. So this derivative of psi of E is actually the one which is going to contribute to this integral. So I actually need to perform my Monte Carlo calculation with more than just one classical integral. So the first part here is the one which I've seen before. I'm doing my metropolis test in here. And now I'm setting up positions, the quantum force, etc. But here now you see that I'm setting up the energy. So this is the expectation value of the energy. This is the derivative ansatz of the wave function. It takes position all, the parameters alpha, beta. So everything here is very much hard-coded for pedagogical reasons. And then you see now that I return the derivative with respect to psi here, which gives my one of these integrals. And then I have the other integral for the energy. So this part and that part are the contributions to this integral and that integral. So these are 2 distinct integrals. Then I need the integral over that term, which I called for energy or delta psi here. So delta psi, that specific term, you can see now it contains the local energy. and the derivative of the trial wave function. So this term here is simply the first equation which we have to, or the first integral we have to evaluate, this specific integral here. So you see, life gets more complicated. And if you want the second derivative, you're going to get even more integrals. And you see quickly now why you don't want to do that. So the energy minimization part is this specific function here. So I set up two parameters for two for number of particles. I do this in 2 dimensions. And then I'm setting up a parameter, this learning rate, which we call gamma in the lecture notes. I do 50 iterations. And then what you will see now when I do these iterations, you will see now that it prints my optimal alpha, which is close to 1, because the system is weakly interacting. And then there is a parameter beta for the correlated part, which is 0.3. And you see the exact value. This is a system which can be solved analytically in 2 dimensions for 2 particles. The exact energy with a frequency equal to 1 is exactly equal to 3. So you see that when I do this now, it brings me to the minimum rather quickly, but you see that the gradients are not 0. So this is the derivative of the energy with respect to alpha, and this is the derivative with respect to the parameter beta. Ideally, they should be equal to 0. Notice another thing here, that what I've done here is actually a very sloppy thing, because I didn't put in a while statement, which says that if these gradients are less than a given number, I should stop. So on the whiteboard, I put up the full algorithm. So this is just a quick and dirty fix. The results will also depend on this quantity, which is actually the second derivative, the inverse of the second derivative. That's this parameter eta. So we can change the number of derivatives and put iterations and put 100 and just see if that changes. So that's going to take more time. Also, note that the evaluation of the integrals, which are all 4-dimensional integrals, because I have 2 particles in 2 dimensions. So the integrals are 4-dimensional. And I'm just making the evaluation with 10,000 points. You will also see that I'm starting my calculation close to the minima. So the minimum is roughly around 1 for alpha and 0.3 for beta. So if I were to start at a different point, it would take me much more time to get there. Now you see now I did 100 iterations. My derivative for alpha is getting close to 0. The minimum have changed. So in the previous calculation, because this is also run stochastically, so that means that every time you run it with a different seed, it gives you a different minimum, slightly different. The value, which is 3.0 exactly, you see now that your Monte Carlo calculation with a minimal answers for the wave function is actually bringing you pretty close to the exact answer. So this is not bad at all. Actually, I would say that when you then calculate the standard deviation, you will get a standard deviation at the 4th digit, which is actually not bad at all, if you think of how simple this was. When I see these things with Monte Carlo calculation, I get impressed. Now, one thing you can do then is to replace this very brute force method. So this is actually my iteration. I could change the learning rate. So one of the standard brute force approaches is actually to run this for different learning rates. But you can also update them with these methods like Adam. You can do a stochastic gradient descent if you want to, especially for you who's doing machine learning as well. Stochastic gradient descent is pretty common. And you would see that when you have many parameters, people often tend to do that. Although here, in quantum mechanical simulations, we are very lucky because most of the energy functions we minimize are convex functions with one global minimum for every parameter. That makes life very easy. Now, Broyden's algorithm it's actually Broyden, the BFGS. You can actually change that. This requires some modifications to the program. Now, what I did here was to bring in the same function, the calculation of all three integrals. Now, these functions in general, and this is something you need to think of when if you're using C++, for instance, or Fortran, is that many of these programs require a function for the derivative and a function for the function itself. So the change here is that I've written one function which calculates the energy and one function which calculates the derivatives. So you would see then the same thing as before, the wave function, the derivative ansatz, and then the quantum force, etc. And here I calculate a function itself, which is called the energy derivative. So what I'm doing now is simply, as you can see, it contains this delta psi, the derivative, etc. And then there is a function which calculates the energy. So I did this also in a brute force way. So that when I'm using, instead of my own function, I'm using minimize from scientific Python. And then you can just plug in the method. So BFGS is Broyden, Goldberger. Oh, I always forget the names of these four guys. Yeah, Shannon and yeah. I always, so please, I hope they don't hear me or they don't see these videos and they don't get offended because I remember Broyden. And Shannon is easy to remember. So this is one of these cases, you know, sometimes you never learn a name. The person can repeat the name again and again to you. It's just like, I can swallow phone numbers, but then there's a phone number which I never remember. There are things you can't explain always. And in my case, I never remember the names of the two middle guys. But here you will set a tolerance, which is 10 to the minus 4, which is used in the iteration. And you would start with a guess. As you can see here, we do a seed here, we do a guess of the values, 0.9 and 0.2. So this is the array of my parameters. And if we just rerun this, you can now see that this is going to converge rather quickly. So it's normally pretty fast. It's going to take a little bit of time. And you see now that the energy is actually pretty good. It used 4 iterations. It did function evaluations 34 times, gradient evaluation 16 times. And these are the optimal parameters it finds. So what you will see every time you run it with different seeds, it will give slightly different values. So if you increase the number of the Monte Carlo cycles which you use, suppose we start with 100,000. So we could just see if that changes things a lot. So let's see what happens and just rerun it with 100,000 Monte Carlo cycles. It's going to take more time because you saw it did pretty many gradient evaluations. So this, yeah.
Can you see the energy derivative means that you have an energy derivative function of it?
Yeah. Yeah, because this method requires that there is a function for the function itself, which is the energy. Yeah, so it just returns the value. So if you have a function f of x, so if you want to find the minimum of f of x equal x squared plus 10x, then you have to have a function for the derivative and a function for the function itself. And these x's are just your initial guesses. Yeah, in 2-dimension, then it's just a vector with 2 entries. So if you have 100 parameters, then this would just be a vector of length 100. Yeah. That's for the Monte Carlo calculation. So the seed. So the one which starts the Monte Carlo piece is the energy here. and then you call the energy derivative. So if you look back at my example up here, then I had baked everything into one code, right? So it means that in this specific case, what you would do now is that when you find these parameters here, and as I said, we run the calculation here with just 10,000 Monte Carlo cycles. Then when I have these parameters, I would say, okay, I am happy with these derivatives. I can live with that. And now I start the big Monte Carlo calculation. So instead of having just 10,000 iterations of Monte Carlo cycles, I could do 1 billion if I want to. Also because you want to have a standard deviation which is as small as possible. So the more Monte Carlo cycles, the happier we are. So one thing which many practitioners actually do here is that they actually sloppily don't include the standard deviations of these integrals. So this is just meant as a way to generate a minimum and then calculate the expectation value. So when you run this in parallel, you would actually have many calculations, which then will find slightly different minima because they will be initialized with different seeds. So it means that you would start with the values which would not be the same. But then at the end, if you run 100 calculations in parallel, you would take the average of all these 100 calculations. And that will be your final energy estimation. So this serves only as a way to get to the minimum without wasting too many cycles on points which are no interest because you're not at the minimum. Does that sound reasonable? Okay. So I was wondering about one thing, since we could now end the lecture by discussing Broyden's method, but the alternative could be that we actually just start doing the lab session instead. And then I can just bring up, because I would need a little bit more time than just 15 minutes. So we could just bring that up next time. And then we'd rather stop now. And then we spend more time on discussing programs, etc. If that's okay. I hope you've gotten the basic philosophy. And then next week, or I can just put it into the lecture notes here and show you how Broyden's method is derived, if that is okay. Because I will need a little bit more than 15 minutes to go through that.